today I want to talk to you about the wonderful combination of function-reactive programming, FRP, and replicated data types, RDTs. This is a trend that has been observed in both industry and academia in the last couple of years. If you're interested in REBLS, just talk to some of the people in the room, they do amazing stuff. If not, just keep in mind that a lot of applications these days that do things like collaborations, setting synchronizations, and offline availability are using some form of combination of these two topics. As a disclaimer, this talk is from the perspective of the Rescaler project. So it's both an update, but it's also highly biased. Just keep that in mind. To make things a little bit more concrete, let's talk about what collaboration, one of these central issues, is about. You may all know this case where you want to collaborate with one of your friends on some shared document. And obviously the way you do that is you edit the document and then send it by email to your friend, who opens it, merges the changes manually, and sends you an updated version back. This doesn't really scale that well to more people or to more updates. So what we really want to do is make use of our connected devices and have this collaborative workflow automated. But there are two main challenges in this area with automation, which are changes over time, which we call interactive, which is the fact that the application no longer is in control of when it receives potential update, but rather the user or the external environment forces these updates to happen. And the other is changes at different locations, which we call decentralization, which is about the fact that, yes, really devices are at physically different locations because the users are at physically different locations and want to work where they are. But in addition to these challenges, we also have to deal with the elephant in the room, which is that we have existing sequential programming models that are really, really good, both for sequential code and sequential data structures. And we don't want to give up all of the quality we have there. We want to keep using the good stuff. And a lot of challenges with decentralized and interactive systems have been from people trying to port over sequential concepts, but in a way that didn't work out. So this talk really is about the reconciliation of both the challenges with sequential paradigms and the new parts we need to make this happen. So first, what FRP does is lifting sequential computations to a time-changing domain. This sounds a bit abstract, so let's look at a concrete example where we want to display a list of tasks to a UI. So we define a state type as an immutable data structure, here just a list of strings. And then what we want to enable programmers to do is just to define some sequential code written in whatever paradigm they want that transforms the state to the HTML, which describes the UI. And what Rescaler or other FRP libraries then allow us to do is to take this immutable state and put it in an abstraction to make it time vary. In this case, a var. So var is a time varying value that has some initial state, and then later you can transform it to produce a new state with this imperative transform method. And the lifting part, in Rescaler you have this as a literal operator, which allows you to lift the sequential code in such a way that you can apply it then to this time-changing state. And the result will be a new time-changing state, but now of HTML instead of state. And what FRP libraries often are about is making these liftings composable, efficient, incremental, and so on. Here we can see just a little glimpse of that because we pass the result to this render function. So we use this time-varying state just as a normal value, composing it easily with other types of abstractions, here a function. Such imperative state transformations are very common in libraries such as Facebook's React, but we don't really like them in classical FRP because they kind of don't allow us to track the connection between what caused this change and then the actual state change. So we have one more abstraction, which are events. So again, we have our state type defined as before, but now in addition, we have a an addition event and a removal event, which are events of strings, the names of our tasks, and events of positions, the elements in the list we want to remove. We don't really care how they are defined. We assume they somehow come from the UI library. But now, instead of defining our state as a kind of imperatively changeable thing, we define our state by folding, starting in an initial state, the empty list, and applying action handlers whenever one of several events occurs. So when the additions event occurs, we take its value, this string here, the text, and append it to the current state, producing a new list that has this value appended. Similarly, when the removals occur, we delete the index, producing a new list that has this element removed. And these new lists are then used as the new state of default. This again produces a signal of state, which is a time-changing value that's fully defined by its right-hand side, which we then again can use in our lifted function. And that's great, because now we have an essentially sequential-looking specification of a concurrent program where events can interleave arbitrarily. And our runtime will then take care that no matter in what order events are received, they are executed conceptually one after another, resulting in this linear timeline. But what about decentralization? Obviously, in a decentralized system, we cannot just linearize the operations. If we try to do so, we get a logically centralized sequential execution, where yes, operations are executed on different devices, but none of the devices can be offline because they always have to coordinate with whatever represents the centralized instance. So we have to allow devices 1 and 2 to independently apply the operations, say A and C, to result in these diverged states. Designing a system to correctly deal with divergence is quite hard. So to make the life easier for developers, what we need to ensure is that when we can exchange messages, then we can merge these states in such a way that if we merge all of the states together, we end up in this final consistent state. The great thing about replicated data types is that they provide this diverged then consistent semantics, which is called dimensional consistency, but they do so using a data type like API, specifically a sequential data type like API. So developers can keep using them as they have been using the sequential data types without having to worry about all of this, this concurrency going. So you may be wondering, so is it hard to implement these RDTs? Well, here's an example of a replicated counter implemented in with our implementation strategy in Rescaler. So all of this is just plain Scala code defining an immutable data structure called counter. You can see down here how it's supposed to be used, right? So you say counter 1 is the 0 counter, and then you say counter 1, we add a value of 5, producing a counter 2, which has a value of 5. A reminder, we always use this paradigm of immutable data structures. So adding 5 to C1 does return a new state, right? It's not mutating C1 in place. And a very typical way to implement replicated counters is to not use a single integer to store the value, but rather use one integer for each replica ID. So a map of replica IDs to the value of that replica. And then the value of the counter is just the sum of all of the values in the map. And to add some amount to the counter, what we do is we get the value of the current ID from the map, defaulting to 0 if it's not present, and add the amount we want to add. And then we return a new counter with a map that assigns the new value to this replica ID. We can implement more complex data structures, for example, a pause neg counter, which is a combination of two counters, a positive counter and a negative counter, which now allows us to not only increment the value, but also decrement it. The value is just the difference between the pause counter and the neg counter, and adding is implemented by essentially a case distinction, incrementing either the positive or the negative counter, depending on whether or not the amount is positive or negative. Now that you've seen how to implement your replicated data type, you may be wondering, but how do we merge them? And the answer in our strategy is we use lattices. A lattice of A, so this would be a lattice of a counter or a lattice of a postNEC counter, is an interface that has just a single method, merge, which takes a left A and a right A and produces a new A. And we only require that this function is associative, commutative, and idempotent. Now, without going too much into the details, essentially what method is trying to solve is a problem that's very hard if you do it in a network layer. Namely, if you replicate state, it's very easy to ensure that each device receives each update message at least once. But it's very hard to ensure that it receives the update messages in a specific order and that it doesn't receive any duplicates. So instead of solving these problems on a network layer, we solve this problem semantically in this merge function. These three properties mean that it doesn't matter in which order or how often you merge the same thing, the result will always be the same. Now you may be wondering, so aren't we just moving a lot of complexity into the merge function? Well, the good news is Rescaler generates merge functions for most data types automatically. Specifically, we can generate merge functions for all primitive numeric types, for sets of A, for any type A, for maps of A to B, given that we already have a lattice of the value type B. Similar for tuples of AB, given that we already have tuples of the components A and B. And we can also generate lattices for arbitrary case classes, given that all components have lattices. And finally, in addition, we do have a library of common RTDs implemented as kind of part of the Rescaler standard library. This is most of what you need to express arbitrary immutable state and get a lattice for free, which is really great. So now we're wondering, what is this magic? What do we lose? What are the trade-offs? This is too good to be true, right? And yes, there is a trade-off. Specifically, because we automatically generate merge functions, there may be operations on the existing data types that have no effect. For example, we do generate a merge function for sets, standard Scala, standard library sets, which do have a remove operation. So if we have a set containing the values 1 and 2, we can remove the value 1, resulting in a set 2. However, because when we use this in a replicated context, we will merge this result back into the current state. So the current state was 1, 2, and the result was just a set 2. When we merge them together, the result will again be the set 1, 2, ignoring the removal. And it's something developers, when they design their data types, such as the counter and the postNEC counter, have to keep in mind. This is why the postNEC counter exists, because if you were just to add a negative value to the counter, this addition wouldn't have an effect due to the way the search semantics on the integers is defined. However, what we do here is we trade developers having to reason about the design of the data structure in a sequential context for them not having to reason about partial failure and all possible concurrent execution of the system. And this is a very good trade, because design is something you can just work on and get right at some point, whereas partial failure is something that just has infinitely many cases and you will never get this correct. And this is also what the combination of FRP and RDT brings us, because FRP really allows us to think about the now instead of thinking about all times and all possible interleavings. And similarly, RDTs allow us to think about the here instead of everywhere, again, and all possible interleavings. And when we combine them, we don't have to think about all times and everywhere. We really just can program things sequentially in the here and now. And that's really great. And basically, we're actually done already, because we can just put our replicated data types, which are immutable data, into our time-changing state, and that will just work out. However, I want to add some syntactic sugar to make this look even a bit nicer, and also so you get a feeling of how it works. So this is the FRP code you have seen before. Nothing has changed, except we now have these conspicuous-looking empty spaces. So what we do to replicate this task list we had before is, so we do it in 2 steps. One, we just redefine the state to be a replicated list up here, and then also the fold will be initialized with an empty replicated list. We need to use a replicated list here because the standard list doesn't track enough metadata to merge it correctly. The replicated list does. But otherwise, the replicated list has the same API as the normal list, so you can also append elements, producing a new replicated list with the element added, and you can delete elements at a certain index, producing a list that records this removal, which when merged is properly kept. But otherwise, you can just keep using your time-changing state, pass that to your lifted sequential code, produce the HTML, throw it into your libraries, everything works as before. Now, this example obviously is not yet replicated, right? Because we just forward over a local program, nothing changed. So we do offer some convenient syntax for replicating forwarded state, which is a replicated forward. It looks exactly like before, except that in addition to the initial state, we now also provide a binding, specifically a named binding that essentially tells us under which name we publish this replicated data type. So semantically, what the replicated fold does is, as a normal fold, when some event occurs, it triggers this action handler, which produces a new replicated value, which is then merged into the current state instead of just replacing the current state like in a normal fold. And then also the result will be published for this binding name, this binding topic, such that other peers can receive these changes. And these peers will then apply the changes essentially like they were a third branch in this fold. So any remote actions that they receive are just merged into the current state of the fold as any local changes. And this is super powerful because in a normal system, you have the problem that when you receive these network messages, you have to keep track of what you need to update. But because we already use FRP, which already has this time-changing abstraction, we don't need to change any rest of our program. It just updates as it updates any change. What I've not talked about in this talk is that we also have formalization and proofs. Nothing fancy, but they do the job. Our implementation has shown good performance. Particularly, we do not have a common issue where state sizes grow indefinitely. And also our network communication infrastructure enables encryption and authentication on the data type level, which in particular means that you can replicate data types over untrusted intermediaries, such as cloud providers, without them being able to modify or inspect your state. This concludes the talk. If you want to see more FRP plus RDT goodness, go to rescalalang.com. You can find all of the code and the implementation there. Lots of documentation is still missing, so now would be a great time to ask questions.
So I think one of the speakers is in Remy, one is in yes. Could you use the microphone?
I can hear you, but not that well.
This is Peter Van Hardenberg. First of all, that's really nice speech, great introduction. I'm curious what the set of replicated data types you've implemented so far are.
Well, you know, I had lots of students do this, so I don't quite know. But we have the basic things like last writer wins registers. We have this RGA, which is the replicated list. I think the RGA is one of the more complicated, interesting things. And then we have a huge research block on basically all of this delta replicated types with dot sets, tracking causality, doing efficient incremental things for mostly standard types. Also causal last writer win things, causal multi-value registers, causal list tracking. We don't do any more complex data structures. Like in AutoMerge or YJS, you would expect to have like these JSON tree data structures, because what we expect people to do is really build their own their own RDTs out of essentially case classes, maps, sets, and composition thereof, because you can arbitrarily just nest RDTs in the system and we generate the merge function automatically. And that makes it often, like, it's not, for a lot of domain modeling, it's actually much easier to just model your own data types, implement them, and not use any of the standard library data types at all, except for lists, which you often need.
So in that case, then, how do you handle change over time, migrations, etc., when you have this sort of closed data type for the application?
No, so we don't do any. So if I got you correctly, if you change kind of the code, if you change the implementation, then they are not compatible anymore.
Do you have guards around that, or is that just here there be dragons?
So the usual way that we presume a rescaler program to be deployed is that you compile it from a single code base, right? And then usually you want to have
simultaneously replacing every
yes,
cloud
yes.
instance simultaneously.
Yes, that is the usual expectation. It's a good point, right? I'm aware of the issue. In my case studies so far, I hadn't had the problem yet, because usually kind of for a lot of applications, if they have data they need to manage over a long time, you kind of want to store it to disk anyways, and you have to think about your formats kind of manually anyway. So you model just your data type as you would normally model, be careful about all of that. And then you kind of still get the RDTs for free, because everything is just an immutable data type, and the RDT kind of inherits this long form thing from what you did anyways. But yes, for a more like business industry ready implementation, we would need some form of better checking of, okay, these are not the same version built in. It's not something that can't be done. Like our applications already kind of exchange version strings, but we like just checking would be easy.
With the bidirectional lenses work, but it seems like what you're doing in Rescala would be a really natural fit in sort of a higher quality functional language. I think you could make a much more elegant solution than we could build in TypeScript with JSON schema. The other question I have is just whether you're seeing like students or independent people adopting these. And one of the open questions we have with AutoMerge and our work in this space is there's sort of this trade-off between how many tools you give a user versus how simple you keep the interface. And so far, the AutoMerge hypothesis has been to kind of try to hold the line and say, no, it's just JSON. Don't think about last writer wins or numerical max, or just as simple as possible interface. And you're saying, well, actually, it's nice to be able to model more complicated relationships and types. And I'm wondering whether you're finding your experiments are making that easy to understand. Are people struggling with it? How much value are your users getting? Are they always doing the same things? How's that playing out?
So, so we have a lot of students currently that try these things out. Some of the things are still experimental, so they struggle a bit with documentation. But for what I've noticed is that some of the students, like about half, they just implement data structures. They don't think about distribution at all, and it kind of just works out, right? Because you kind of just implement methods. Like oftentimes you just implement something. You like for the counter, for example, we implement this ad. This is something we do expect the developers to do, the students to do, and some of them that are more used to like this functional data structure modeling, they do it just fine, and then everything works out. And then sometimes students want to use like something that's not an RDT, and then they're always like let's just use the last writer wins for that. So this is the most commonly used data structure, I think, where it's like something you don't normally have in a sequential program. And I think there the main issue is that we have like 4 different implementations of last writer wins. So I think this is the problem of we should provide a bit of more guidance of which one to use, because they always pick the most complicated one and then it doesn't behave as they expect. And I'm like, maybe pick this other one. But other than that, like other than the confusions of just the normal sequential programming paradigm, I haven't seen that much issues with the kind of the replication model, the distribution aspect, and any of that yet. This may be because a lot of the applications we focus on are very naturally naturally monotone, right? Naturally just add things into a collection and then it works, right? That's a lot of the things we currently experiment with.
What applications your students are building?
What was that?
What kind of applications are people building?
Right. So we have one example is we have an internal time tracking, a hiring process workflow management thing that some people are trying out. Then we're experimenting with some low code to no code UI generating stuff. Let's see how that works out. We do have some debugging, well, not debugging, visualization for reactive programming, which we are trying to distribute now. What's the third problem? Things like that. So it's a lot of applications that are not, they don't solve super hard distribution challenges like the text editing, right? Which is just always a nightmare, even if you don't look at the any of the thing the program needs to do and just look at the data structure itself.
To say nothing of rich text. Well, I won't monopolize it anymore here. Very nice to see your work. Thanks for sharing.
Thank you for asking.
Any question? Okay.
Okay, hello. Yeah, thanks for the nice talk. So you mentioned things like encryption and maybe like distribution for the data types. So I was wondering, just like practically in your work, to what extent are you focusing on the RDTs versus tools to actually make kind of in an encrypted collaborative software, like the environment around the RDTs?
So you're asking about the encryption. What was the core of the question? I may not have.
Just like in terms of your focus, like what you're building, are these either now or going forward? Are you more thinking about the RDT side or like the tools around the RDTs, like the encryption and stuff like that?
Are we working more on the RDT side or on the tools around side? I'm not sure if I see, like, for me, there isn't like a type of RDT, right? I call these RDTs, there's like lots of different implementation strategies for RDTs. We use basically something that's very similar to state-based or delta state-based CRDTs, but we could use any kind of RDT implementation. We're always looking for new things we could integrate there, right? But that's more of a new algorithms, new things. We don't, I think we've never designed like something super our own, so we've never really looked into that. We're mostly on the kind of making the things more composable, better usable in the language and stuff like that. I'm not sure if you would call it tools. Also, the encryption, for example, is just another RDT. You can put other RDTs into and it will encrypt things. It's just one more layer of data structures, which is kind of nice. But that's kind of the focus in this area. It's really just like what we wanted to do is we wanted to make RDTs compatible with FRP. That was the original goal, and then we figured out, hey, this works really, really well from a programmability side.
Okay, thanks.
Okay. Any other questions? No? So let's thank the speaker again.